Thank you, the organizers. It's a real big pleasure to be back in Garching. I'm meeting some familiar faces again. Today I will be introducing you to the J+ survey. This is more or less the sketch of my talk. So half of the talk will be describing the site, the strategy, the survey itself, and then I will try to scatter some of the scientific results that we have obtained over the last 8 years or so, right? And then I'll give you some slides on how to access the data, because most of the data is already public, and a flash about the future of this survey and some other parallel surveys that will be addressed during this meeting. So first of all, a little bit of geography, Spanish geography, right? Here, I use the mouse from the computer. Here is the city of Teruel. Teruel is probably the smallest capital in Spain, and has traditionally kind of, been complaining because of its isolation. It was really hard to get there, right? If you zoom in, Teruel lies between, Zaragoza in the north and Valencia here on the east. And part of this isolation was due to, because around here, there is a sierra called Javalambre Sierra. In the last 10 years or 12 years, we have built a new astrophysical observatory, Observatorio Astrofísico de Javalambre, OAJ, which is about 2,000 meters above sea level and has, two main survey telescopes. This is really an isolated area. If this is it's fairly old already, 6 years old, but things haven't changed much. If you count the amount of people who live there, it's actually below the amount of people who live in northern Scandinavia. The amount of people is like in Scandinavia, you have like 1.9 inhabitants per square kilometer. Here it's slightly below that. So it's really isolated, and it's really dark too, right? So this is a good place where to build an observatory. The median scene is around 0.7 seconds. And as you see, there are two survey telescopes. This is the Javalambre Survey Telescope and the Javalambre Auxiliary Survey Telescope. Today, I will be talking about the latter one, the T80, right? It's called T80 because it has 80 centimeters of diameter, the main mirror, and it mounts T80 cam. T80 cam has one single CCD from E to V of about 1 million pixels. And it has this filter shutter unit, which can carry 2 trays, each tray carrying 7 different filters, right? One remarkable feature about this camera is that the field of view is 2 square degrees, 1.4 degree on a side. And in combination with this set of medium and wide optical filters, gives you a hint of what is this niche, the strategy that we are following from this observatory. We want to conduct wide field optical surveys with a lot of narrow or medium band optical bands that provide a lot of physics, a lot of information about the physics of whatever object we look at. This is indiscriminate. Any object that we find on the sky will have measurements in all these filters. And this provides a lot of information, so I'll try to show next. So on top of the 5 broadband filters from Sloan, we have these narrow or medium band filters, which are strategically chosen to sample, key features of the spectra, O2 line, the magnesium triplet, the H-alpha, calcium triplet, and so on, right? The typical width is, 300, 400 angstroms. And itself, J+ was conceived to be a calibration survey for a bigger survey that Javier Fenara will be talking about this week. But by itself, it has become its own survey with its own science, as I will try to show next. So, well, this is data release 3. We released the third data like a year ago, which is about 3,000 square degrees. From this plot, you can see what is the footprint. So we have a big part on the northern sky, and then we have like a big other chunk in the southern sky. And this, we have like 47 million sources, roughly depending on the depth. Half of them stars, half of them galaxies, depending how deep you go. But for many of them, we have actually photographic PDFs, right? For a significant fraction of them. For the stars, we get no sense, right? But for the galaxies, we have a PDF, which I'll show next is not bad at all, right? Precisely because of these narrow band filters. You can see how deep we go here. So typically, we have like detection band at the R, and the G and R bands are a bit deeper, go down to 22 AB magnitudes, and the rest go like 21, right? This is for every pixel in the sky, right? So, it doesn't make much sense to get very deep on the broadband filters, much deeper than the narrow ones, right? So this is roughly the amount of time, the ratio of narrow to broadband time is 1/3 or so. What is remarkable about this survey, and this is excellent work done by Carlos López San Juan, in the last few years is the calibration. So this survey has been calibrated absolutely in an absolute way, right? And the uncertainties that you see here are at the level of millimagnitudes, right? So depending on the band, you have this uncertainty in the magnitudes. And this has been done because of the existence of Gaia, because of the fact that span stars DR1 covers the whole footprint of J+. So what he has done is he used Gaia data to isolate a good sample of stars, right, on which is build a stellar Loci. And then the G, R, and I bands have been calibrated to pan stars. And then all the rest of the bands have been used, are using the stellar Loci to actually shrink and calibrate using the stellar Loci from the Gaia subsample of stars. Then he found that there was like in the CCD some trend in the calibration that he corrected for. And then finally, the white dwarfs, which are very precisely described by these narrowband filters in the blue band, in the blue area of the spectrum, are able to provide absolute calibration to the entire set of data, right? You can actually see the two populations of helium and hydrogen white dwarfs, and you can distinguish them. Actually, we see them in such a great detail that you can even able, as a bonus, to characterize the spectral evolution of these sources depending on the temperature. Then, we can tell the amount of helium on these sources depending on the outer temperature, right? Let me just flash some science cases. With these narrow or medium band big filters, these are very sensitive to spectral. These spectral features are depending on the physical parameters of the stars. So out of millions, tens of millions of stars that we have developed different machine learning algorithms that are able to provide measurements for the gravity, for the temperature effective temperature, and for the metallicity. And from this huge sample of tens of millions of galaxies, we're able to actually isolate which are the ones more likely to be extremely metal poor, right? And these algorithms are improving over time and becoming more and more precise. So, this is already a couple of years old, but out of 11 candidates that were followed up spectroscopically, all of them had metallicity below -2, and 65% were confirmed to be with metallicity below -2.5. Just as an example, right? These narrowband filters also have the H-alpha filter, which is ideal to trace and to monitor the star formation rate in the local universe, right? So in combination with the other filters, we could fit an SED for all the galaxies around in our neighborhood, and we could, provide measurements of the local star formation rate versus stellar mass, and compared to other surveys, finding excellent agreement. Those narrowband filters can also be used to trace the emission in particular lines, particularly the O3 line, the bright O3 line. So what we did in this different work is trying to target all sources in our nearby, just below redshift 0.06, which having very, very bright emission in O3, right? So of course we had to use all the data like SDSS or WISE or unwise in order to discard interlopers, in order to discard bright Lyman alpha emitters at high redshifts. At the end, we came with 466 streamline emitters in O3. Out of which 400, most of them were actually new. And you can see that they were blue compact objects in the nearby, right? Near from us, right? And this way of isolating these bright emitters is way much, like 20 times more efficient in terms of density than all other broadband services so far. But one cannot restrict oneself to the low redshift universe. Now we're going well beyond our galaxy, even though this session is for the inner galaxy, right? You can use these narrow band filters or medium band filters to actually isolate Lyman alpha in the very distant universe, right? So we developed another pipeline to actually isolate Lyman alpha emitters at high redshift, right? So using these medium or narrow band filters, we predicted the amount, where we developed a strategy to actually get rid of the interlopers at lower redshifts. And then we actually conducted a follow-up program using Gran Telescopio Canarias in the Canary Islands, which worked very well, right? So 80% of our candidates were actually high redshift quasars, 67% in the target redshift range, right? So you see that, we had like from 24 objects that were observed, 15 of them were actually at high redshift, 4 of them were at slightly lower redshift, and then we had some other objects that had some prominent emission lines, which were kind of confusing. But the program is working really, really good, right? So the fact is that this, because this was on DR1, which was 1,000 square degrees, we could actually measure the extreme high luminosity tail of the luminosity function for these Lyman alpha emitters, right, by first time, with very at redshift, depending on the redshift, right, but at redshift 2.25, 2.37, 2.54, and 3.24. You see, this is our data. And what we see is that this population is necessarily associated to a family of objects that are close to quasars and AGNs, which are distinct from the, from the star-forming Lyman alpha emitters, the galaxies that are not quasars, right? These have a Schechter function that is different from the ones. So this is really pointing to something that is more or less accepted in the community, which is that at high redshift, at redshift between 2 and 3, most of the Lyman alpha emission is actually driven not by star-forming galaxies, but by quasars and AGNs if we restrict to high luminosities. Luminosity is about 10 to the 44 ergs per second, right? This is a very important result from this collaboration. But so far, I've just shown results. Okay, perfect. Just immediately inferred from the narrowband filters. But these narrowband filters, in combination with the broadband ones, actually provide very accurate photoreshifts, right? So we have photoreshifts of the level of 3% for R below 20. And even you can, use a notch parameter that's telling us the quality of the photosys. You can restrict your sample much more at the, by imposing a cut in odds, and then you end up with samples of galaxies which have very accurate photoredshift of the order of 1%. This is a work. I'm a cosmologist. I'm biased here, so I'm trying to do some cosmology with such a narrow and shallow survey, but still in the limit, right? But this is working very, this is promising for larger surveys. As we grow in area and we grow in depth, things will get better, right? So here, we were able to do tomography in low redshift universe. We are using two statistics. The one is the standard 2D clustering. The other one is a new statistic, a new cosmological observable we have come up with, which is called angular redshift fluctuations, which is sensitive to the actual photometric redshift error at different redshift shells. So here, every point here is a different redshift shell. We measure what is the typical photometric redshift error, which is at the level of 1%. It slightly increases with redshift. And we can also measure the bias of the galaxies. We're in the limit of measuring the peculiar radial velocity. The photometric redshift error are too big to be measured in a single galaxy, but as you integrate over large areas, you may be able to see the bulk flows. If we had a bigger cosmological volume, probably this peak would, we'll be able to isolate and measure peculiar velocities, but not yet, right? So I think I'm getting there. Just a few slides showing data is public. It can be accessed here. Here it can be accessed in many ways. You can have a Sky Navigator, which is beautiful. You can just click on any source and you can get the photo spectrum. But you can do the ADSQL query. You can query by name. You can query by search cone radius, whatever you want to do. And if you have suggestions, just log in. There is the department for actually data storage, who are willing to take suggestions and help you with the data, right? And just a couple of final slides. This is J+. This is the J+ filter design. But now we're transitioning from this to this, which is the J+ survey.